Robotic vacuum cleaners have become a standard feature in many homes. Their task to clean rooms lends itself for reinforcement learning. The task of the robot can be described as an episodic MDP. From initial state, the charging port, the robot gets positive rewards for cleaning dirty surfaces and negative rewards for recleaning previously cleaned surfaces. Additionally, a smaller negative reward can be used to penalize time or battery usage. The episode ends after the whole room is cleaned, which yields a high positive reward, or if the battery runs out after some fixed time, which yields a high negative reward. Such a vacuum cleaning robot is modeled as a so-called differential drive robot, which has nonlinear dynamics. However, for the purposes of this project, we will simplify this task to a so-called two-dimensional grid world problem. Imagine the room being a square grid similar to a chessboard, with the robot starting in the charging station in the upper left, shown by a blue dot here. The robot can move to its neighboring fields, which are its available actions. Now recall the reward structure that we've introduced in the beginning. For every action, since we are moving from the start point to a tile we have not yet visited, regardless of what action we take, the rewards are positive anyway. This is essentially the foundation of Q-learning. We are assigning a value to all possible state action pairs and choose the best possible one. In this case, both actions yield the same reward, so we randomly choose to go right. Now again, we can compare our two possible actions, which are going back left or down. This time, however, the two actions yield a different reward. Since going left would bring us back to the start, the reward is negative, so it's the suboptimal action to choose as opposed to going down. It's easy to see that in the end, the optimal policy is to go around in a loop and visiting all tiles, which gives us the largest total reward. In the end, what we want to maximize is the return. This is the discounted sum of every reward at each step. For a robot, what we want to learn is the so-called Q value, which can be learned iteratively through temporal difference or TD learning. Especially at the beginning of training, when we don't know a lot about our environment yet, it's important to select a good amount of random actions, so that we don't get stuck in training. This is the learning framework we want to use to train our robotic vacuum cleaner. Next up is training the robot to hopefully clean the room as efficiently as possible. Tuning these hyperparameters we've introduced will play a crucial role in training the robot. Here you can see the robot training with a learning and exploration rate of 0.5, meaning that the robot takes random actions half of the time. What's happening in the beginning is that the robot is exploring the map and trying to bring the Q values for each state and action to some converging value. In the beginning, we have to initialize the Q value for each state and action, which can either happen randomly or optimistically. In this project and for this problem, we have found that optimism in the face of uncertainty usually works. Now, let's look at another instance of the robot learning uses some other hyperparameters. Here in this case, the robot has an exploration rate of 0, which means that the robot never takes random actions and always follows the maximum Q value. A few main challenges can be seen here. The robot often gets stuck in between two states, so that it switches back and forth between them. This is the robot getting stuck in some kind of local minimum. This took quite some time to find out and figure out and control by adjusting the reward structure and the learning rate. Secondly, the robot is not actually improving quickly and does not seem to converge to a solution. Thirdly, and this is not visible here, the robot sometimes finds the optimal policy, but then leaves it again to pursue a suboptimal policy. In other words, the robot fails to converge in order to achieve a consistently high return. The remedy for the latter problem was to introduce decaying exploration and learning rates. A decaying exploration rate, as seen here, can greatly help with convergence of a robot's training. After finishing the project, the following conclusions can be drawn. The robotic vacuum cleaner's objective of cleaning all surfaces in the room can be effectively modeled as an MDP, whose structure with rewards encourages the robot to clean dirty surfaces while penalizing re-cleaning of previously cleaned areas. Using Q learning, an optimal policy can be developed that efficiently cleans the given room. Due to the simple grid world structure, training time is negligible, with most of the computational time devoted to visualizing. Without visualization, training for hundreds of episodes only takes a few seconds. Overall, this project demonstrated the feasibility of using reinforcement learning techniques to develop efficient policies for this problem. In the future, this problem can be further developed using more sophisticated algorithms or moving into the domain of continuous state and actions for the vacuum cleaning robot.